Hi everyone. I'm Sora. I'm mainly working for ZK email, but I'm also personally researching some silly cryptography. And today, I would like to introduce a new cryptography that maybe many of you have never seen. So let's go. So today's talk is about private computation with some private state data. So we define this protocol like a trusted party holding a private state data, and the user providing an input want to computer its output of a certain circuit on inputs on the private state and the input data. However, this protocol should not reveal no more information more than the circuit outputs. In other words, each party the protocol should hide the information about the input and the private state for each other. Then, how can we use this kind of computation for the application like with Web 2 to Web 3? So we can use this for using the uniqueness of the Web 2 identity or information with keeping the anonymous property. So for example, we can consider anonymous and unique human ID. So we define this ID as a hash of some random sort and the unique human attribution. So for example, it is your passport number or your iris code. And we can also define its proof of holding the attribution, like proof of passport for your claimed passport number, or a video of your eyes, and this proof says eyes in this video has a claimed iris code, and this eye is also living one. And we want two requirements about this human ID. First one is the uniqueness. So it says each human can obtain only one human ID at the same time for the same attribution type. And the second one is anonymousness. So it says even if some other party knows the your attribution like your passport number, no one can compute its human ID without the proof of holding the attribution. So if the adversary does not know the proof of passport, you cannot compute the proof human ID of your passport number. And and this will be useful for some on-chain application, like distinguishing between humans and bots in the contract, or some on-chain voting where one human has one vote, but it can maintain the anonymous property. Or this is my most favorite application and this is our on-chain death game, where once you die in the game, you cannot join the game again, because this game requires your human ID, and once your human ID is registered as a dead one, you cannot get the same human ID, unless you get two passports. Yes. And we can achieve this kind of application using private computation with private state by setting the random sort as a private state, and user provides the proof of holding the attribution as the input. And this one computes the human ID only if the given proof is valid. And if you are familiar with MPC or FEG, you may think we can achieve that using them. So for example, if you use FEG, the user will compute the proof of holding the attribution and homologically computes the human ID using the encryption of the salt, and also we need a proof of the FEG evaluation using LDCODE's library. And the trusted party will decrypt this encryption of the human ID if and only if the given proof is valid. However, here we have a liveness or strong liveness assumption on the trusted party. So this is significant because if trusted party goes offline before returning the decryption of this encrypted human ID, user cannot get the human ID anymore. So if the trusted party goes offline, the human ID's application does not work. So here, if we can construct a non-interactive version of this private computation, we can solve this liveness problem. Because in this non-interactive setting, the trusted party only needed to send one single message. And this single message allows the user to perform this private computation without the help from the trusted party. But it should not reveal the information about the private state. So can we achieve such non-interactive version of private computations? So in short, it's impossible in your practical way now, but theoretically it's possible using one of these cryptographic theories. And today we focus on cryptographic obfuscation. So IO does not depend on does not denote the cryptographic obfuscation, but IO is one of the cryptographic obfuscation. So so we go to the deep part of the obfuscation. So what is the obfuscation? So it's kind of process to compile some original circuit to a different form of obfuscated circuits. But since this is just a circuit, you can provide some input for the obfuscated circuit, and here its output should be equal to the output of the original circuit for the same input. In other words, it does not change the functionality of the original circuit. However, adversary cannot get non-trivial information in this circuit by observing, even if the adversary can observe this obfuscated circuit. And unlike the heuristic obfuscation scheme, or like JavaScript obfuscation, this cryptographic one says as long as some cryptographic assumptions hold, or then some cryptographic problem is held for this adversary, the adversary cannot get the non-trivial information from this obfuscated circuit. So with enough security proof, we can also embed such as Bitcoin's private key. We can also hard-code the Bitcoin's private key inside the circuit. So this strong security definition is a feature of cryptographic obfuscation. Then, which kind of formally, which kind of security we can define? So actually, the formal definition of obfuscation is called indistinguishability obfuscation. It's IO. And IO says if there are two circuits with a different implementation but with the same functionality, in other words, these two circuits return the same output for the input that the adversary can query, then the obfuscation of these two circuits are indistinguishable for the adversary. So even if adversary knows these two circuits, whether obfuscation of C0 or C1 is provided for the adversary, it cannot determine whether the obfuscation comes from C0 or C1. But maybe you think this security definition is not so useful, or we want more stronger, clear security definition. But unfortunately, we cannot say we can construct some obfuscation which only reveals the information about the circuit or about the circuit output in a plain model. However, in the paper in last year, so this paper says if we can believe some more stronger assumption about the hash function, we can model our ideal cryptographic obfuscation which only reveals the circuit output. So if we use such ideal obfuscation, we can construct a non-interactive private computation with private states in this way. So in the case of human ID computation, we consider a circuit that's where the salt is hard-coded, and it will first verify the given proof, and if the proof is valid, it computes the human ID using the hard-coded salt and the provided humorous attribution. And the trusted party only needed to construct this circuit with hard-coding random sort and submit the obfuscation of this circuit. That's all. And the evaluator can compute this obfuscated circuit just by providing the proof of holding the attribution to the circuit, which does human ID. And to check the liveness, we consider the case where this trusted party goes offline after releasing this obfuscation. Even in that case, the evaluator can still compute the human ID because it only requires this obfuscation, but this obfuscation should be published at the setup phase. So we can say we don't have to value liveness of this trusted party. Then, finally, you may think, can we really achieve such obfuscation? For many years, many cryptographers think obfuscation is actually impossible from well-established standard assumptions. However, breakthrough happened in 2020, and as far as I know, this is the current latest and simplest construction of IU. So, if you believe these top of these three cryptographic assumptions, first one is a running parity with noise assumption. It's similar to LWE, but L distributions are slightly different. And the second one is just says we have some slow random generator with a constant deep circuits. And the third one is a kind of assumptions on binary groups, in other words, assumptions using pairing. And only from these three assumptions, we can construct a functional encryption, which is a more functional version of public key encryption. And using that, we can construct an IO. And also, if we believe more stronger assumption about the hash function, we can construct ideal obfuscation from this functional encryption. So the current status of obfuscation is we believe we can construct obfuscation from standard assumption theoretically, but its concrete construction are still impractical. So I believe next 10 years will be like a progress of ZKP. So it means we will make more practical and practical first construction of obfuscation, and we will have a practical solution for such non-interactive private computation. So I want to contribute such progress. Thank you for listening. Do you have any questions? Okay.
So what exactly is like the overhead of the latest IO results?
So there are many overheads, but one of them is, I think, the step. So one step is our bottleneck is transfer from functional encryption to IO, because its complete idea is so we recursively use our functional encryption. So functional encryption is okay. Sorry. So functional encryption is similar to private key or encryption, but its decryption algorithms only outputs the psychic evaluation of the message in the ciphertext. And the idea of the transform from functional encryption to IO is it computes the encryption algorithms of the functional encryption inside the circuit of this functional encryption. So its repeat process should be at least linearly increased with the input size. And actually, I don't understand the complete flow of the scheme to construct functional encryption from three assumptions. But I think this step will also have some bottlenecks. And okay.
So, would it be possible with IO to, for example, create a smart contract that is like holding a private key and like signing stuff based on some condition?
Yes, thank you for your question. So I think it's possible because, so for example, we can embed hard-coded algorithms which verifies the finalized Ethereum blockchain and checks if some conditions are satisfied on chain. So if we combine such verifier, Ethereum verifier algorithms plus some algorithm to use the hard-coded private key under some specific condition, we can say if there are some events happened on Ethereum and you can provide the proof of finalized Ethereum blockchain, you can use this private key for this purpose.
Cool. All right, let's give Sora a final round of applause.